Hello and welcome to the third in a series of videos on evaluating limits, a summary of evaluating limits. In this beginning video in section 2, we're going to talk about finding limits at positive or negative infinity. All of section 2 will talk about finding limits at positive or negative infinity. So this, you can see these problems are similar to finding horizontal asymptotes or end behavior of a function. And if you remember that, in some cases that is, you can answer the question that way. It might be helpful to remember that when I'm talking about the limit as x goes to negative infinity and I'm drawing a graph, I'm talking about like way out at the end here for positive infinity, and negative infinity would be over here. What goes on with the y value is what I'm asking about when I ask about the limit. Is it going up? Is it going down? Is it leveled off at some value? So here's the notation. The limit as x goes to negative infinity of f of x can be thought of the end behavior of the left end of the function. The limit as x goes to positive infinity of f of x can be thought of as the end behavior of the right end of the function. There are only 3 possible outcomes for the limit. The y value could continue to rise from the end behavior and you get positive infinity as x goes to infinity. Or negative infinity, the y value could continue to fall in the direction you're looking, which makes the end behavior negative infinity, or the y value can be leveled off to a particular value. We call this a horizontal asymptote. That value could be 0 or some other number. In pre-calculus, you learned how to determine end behaviors of polynomials. You learned that by using the degree and the leading coefficient. So the degree of a polynomial is the highest exponent. So you're only interested in the term that has the highest exponent. In this example 6 here, the limit as x goes to infinity of 2x squared minus 8x plus 10, the degree is 2. And that's from the exponent 2. It's unfortunate I chose a 2 for the coefficient here too. The leading coefficient also happens to be a positive 2. But I really only care about the fact that it's positive. So leading coefficient is the number in front of the variable with the highest power on it. So I have a degree 2 polynomial. Now, all even degree polynomials behave either like, the ends behave either like the ends of x squared, where they both go up, or the ends of negative x squared, where both ends go down. So this would be going off to infinity in the left and right. This would be going to negative infinity in the left and right. Now, if your coefficient is positive, this is the case you have, and that's the case we have. And if you graph this quadratic, it's no surprise to you that it goes like this. Its general shape is like that. This is only a quadratic. So the limit as x goes to positive infinity, that would be asking us about this end. So because I have an even degree and I actually have squared, if I had x to the 4th there, this answer would be exactly the same, by the way. If I had 2x to the 4th as my leading term, my highest degree term, my answer will be exactly the same, because every even degree behaves either like x squared or negative x squared, and to determine which you look at the sign of the leading coefficient. So in this case, the limit as x goes to infinity, 2x squared, that is going to equal infinity. Now, we used to say the function rises. When you describe end behavior, we say it rises as x goes to infinity. Now we can say the limit as x goes to infinity is infinity. You should have seen that for polynomials in a prior course. So here's another one, example 7. This is a polynomial. It is a degree 5 polynomial. Now, the other choice, so either both ends do the same thing on a polynomial, or they either both go up or both go down. That happens if you have an even degree. When you have an odd degree polynomial, the ends of your polynomial are going to behave like the ends of either x cubed or negative x cubed. So you should right off the top of your head know that x cubed goes like that. Now, if I turn it around, I just turn the ends around. This is a this is positive x cubed. This is what the ends do. I go to negative infinity as my y goes to negative infinity as x goes to negative infinity. Y goes to positive infinity as x goes to positive infinity. But if I had negative x cubed, those would be flipped around. As I move to the left, y rises. As I move to the right, y falls. Because the graph of negative x cubed is like that, where that's your origin. Okay? So the ends of x to the fifth will behave like the ends of x cubed, but you notice I have a negative in front of x to the fifth. I have a negative, what we call leading coefficient. A coefficient is a number that multiplies a variable expression, or a variable term, I guess. So because I have negative, I choose this. So I am going to positive infinity. As x goes to positive infinity, this function is also going to, so this will be positive infinity out here. This will be negative infinity out here if I draw a number line. This function, as x goes to positive infinity, the function will be going to negative infinity. The other way you can look at these is you can consider, so when you have a really huge number you're putting in for x, it turns out you can ignore all but the highest degree term. So only as x gets large or goes to infinity, the x to the negative x to the fifth dominates. It swamps out all of the rest of the numbers. If you have a huge number and you raise it to the fifth power and you add that same number raised to the third power, you have to go out a lot of significant digits to see what you added. So think of numbers with, 10, 12 digits. You raise that to the fifth power. Now you're talking maybe 60 digits, whereas you raise to the third power, now you're talking 30. Huge differences in significant digits. So you can consider that as x goes to infinity, our function is approximately equal to negative x to the fifth. And you can't really do this in math, but let's pretend x is infinity. Well, what happens when you raise infinity to the fifth? You just get more infinity. So your answer is negative infinity. You just get bigger, right? And notice the negative is on the outside. It's not inside it. And it wouldn't matter in this case anyway because it's an odd exponent. But the negative x to the, what you're replacing, making infinity, is just the x. That's why I did it this way. So you can think of it that way. Is you only need to consider that term and what happens when I put infinity into that. Do I get negative infinity or positive infinity? I could have done that in example 6 as well. I could have said, okay, 2 times infinity squared, what kind of infinity is that going to give me? Or is it going to give me a number? In this case, it's not going, you don't get numbers out of polynomials as they go to infinity. This will give me a positive infinity. There's no such thing as 2 times infinity. You just get positive infinity. So that ties together a little of prior knowledge about end behavior. The next piece of prior knowledge is horizontal asymptotes. Horizontal asymptotes of a rational function where you had one polynomial divided by another. Now, in example 8 here, 5 is a constant. It's a degree 0 polynomial, essentially. But what you did here, when you found horizontal asymptotes, was you had some rules. You looked at the degree of the top and you looked at the degree of the bottom. And if the degree of the top was higher, you had no asymptote. If the degree of the bottom was higher, your asymptote was y equals 0. And if the degrees were the same, you made a ratio out of the coefficients. What you're really doing there is separating out the top and the bottom. And as x goes to infinity, your function approximately becomes, so we still have that negative in the front, that stays. But you look at the top and you look at the bottom and you take only the highest degree term of each. Well, there's only a 5 on the top, so that's what's there. And the bottom, I have an x squared. Now, let's think about what happens is if you have a very large number. You have 5 divided by a very large number. squared. Infinity is a very large number. Even if it's a very large negative number squared, what happens? In arithmetic, if you take a number and divide it, so I take 20 and I divide it by 10, I get 2. But if I take 20 and I divide it by 1, I get 20. If I take 20 and I divide it by 0.1, I get 200. The smaller the divisor, the smaller the number on the bottom, the larger the result. Well, the opposite's true too. The larger the number on the bottom, divided by 1,000 is 0.02. As I divide by bigger and bigger numbers, I'm going to get more and more decimals here. I just chose this as an example. So as this number gets bigger, the answer gets smaller. Well, this is the biggest number you possibly could have, and so you get the smallest number you could possibly have, which is 0. Now, it doesn't matter that it's a negative number over a positive number. You can approach 0. You're becoming 0 from the left, that's all, instead of from the right. But you get to 0. Anytime you're left with a constant divided by a huge number, you get 0. The constant can be 1. The constant can be 10. It's true that the limit as x goes to infinity of 1 over x is 0. And if I look at in the limit as x goes to infinity of 1 over x squared is also 0. Well, 5 over x squared is just 5 times 1 over x squared, 5 times that. So I can take the 5 out, and 5 times 0 is still 0. Your rules were if the degree on the bottom in pre-calculus is larger, you get 0. Now, you get negative 0 in this case, but there's no such thing. So the limit as x goes to infinity of negative of 5 over x squared plus 1 is indeed 0. Okay, so you have a horizontal asymptote, you have a numerical value there. Another example here, example 9. Now the degree on the top. So it's approximately equal to the limit as x goes to negative infinity. That's a large number. It's a negative number. It's still a large value. I just keep the highest degree on the top and the highest degree on the bottom now, and I reduce. Now, even if I had like a minus 2x plus 3, I would ignore those. I'm only at the highest degree. And I reduce, and I get 3x, x cubed over x squared, gives me an x on the top, over 4. So now, well, I get a 3/4 times a negative infinity. You can't really evaluate negative infinity, but if I have a really large negative number times 3, I get an even larger negative number. An infinitely large negative number divided by a positive number is going to give me negative infinity. Okay? So, we used to say there is no asymptote for this case, but the truth is we get negative infinity. Now, if this had been the limit as x went to positive infinity, my answer would have been positive infinity for this one. So, again, that reasoning, if I have infinity left on the top, I'm multiplying by 3 and dividing by 4. 3/4 of infinity is still infinity. 3/4 of negative infinity is still negative infinity. When I go to example 10, this is another similar. So as x goes to infinity, this is as x goes to infinity, this is approximately the same as the limit as x goes to infinity of the negative. Just keep the highest term on the top. If there had been a plus 1 or plus 3,000 after, I would have still ignored the number because the higher exponent will dominate over x. Now, when I do this, see, this one reduces. I get the negative of 2 over 1, which is negative 2. The limit as x goes to infinity. There's no place to put infinity here. I'm just left with negative 2. So this is a case where I get a number. And when you learn these, you learned as horizontal asymptotes, the degree of the top is 1 and the degree of the bottom is 1. So you just divided the leading coefficients, but you also have to pay attention to that negative outside. So that's another example of finding a limit as x goes to infinity of a rational function.